To oscillate is to swing to and fro, or vary from maximum to minimum. This pendulum, then, is a mechanical oscillator, and its purpose is to help the clock keep accurate time. We have arranged a mechanical oscillator to explain a few basic principles and to demonstrate its relationship to the electronic oscillator. With this device, we can graphically illustrate the action of an oscillator. This felt pen is suspended by two rubber bands, one on the top and one on the bottom, and will act as our oscillator. We'll supply the initial energy by stretching one of the rubber bands, and when it is released, it bounces back to normal. However, the velocity given the weight, the felt pen in its holder, causes the bottom rubber band to stretch a little bit, which will pull the pen back down past center, causing the upper rubber band to stretch again. Or energy is passed back and forth from one rubber band to the other. And this action continues until it finally comes to rest. We've arranged this device on a track so that it will bounce or oscillate up and down. And we have a motor that will cause the paper to move past the pen as it marks the path of the bouncing. In short, this device will record the action of the mechanical oscillator. Now, with the oscillator at rest and we start the motor, the marker draws a straight line, our zero reference line. We add energy, and our oscillator will bounce up and down. The felt pen marking on the paper, drawing a waveform as it plots the action of the graph. Now notice the similarity to an AC sine wave. We can also see that the amplitude of the oscillations steadily decreases from the point where energy was initially supplied. What causes this damping action? What causes the decrease in amplitude? Well, in this case, the action of the oscillator is gradually diminished by the friction of the slide, the friction of the pen on the paper, the force of gravity acting on the weight, and the resistance of the rubber bands themselves. In short, the diminished amplitude on the graph is caused by inherent resistance in the oscillator. Now, only if we overcome this resistance can we make the device oscillate continuously. And since this is a rather crude device, it has a large amount of resistance. We must add large amounts of energy to overcome the built-in opposition. Let me add a little more ink to the felt pen, and we'll see if we can demonstrate this. Start the paper going past the marker. We continually add energy, and if we could add it in the proper amount, we would have a waveform of constant amplitude and constant frequency. Now, our graph shows us that this method produces a waveform of almost continuous amplitude and stable frequency. This is essentially the wave shape we want out of the LC oscillator. Constant amplitude and constant frequency. Of course, this graph does not show that by any means, but it does illustrate the point. All right, let's compare the two. The rubber bands and the weight determine the frequency of the bounce. Resistance causes the amplitude of the bounce to gradually decrease. But if we feed energy to the device, it will bounce continuously. In the LC circuit, L and C compare to the rubber bands and the weight, the frequency determining device. And as you recall, the resonant frequency of the tank can be determined by the formula F sub O is equal to 0.159 over the square root of LC. Or very simply, the frequency is determined by the size of L and C. Now, to be sure you understand how this circuit will oscillate, let's follow the action step by step. First, we'll need a power supply to provide the initial energy. in this case a battery. This switch will allow the capacitor to be connected to the battery or to the coil. If we flip the switch to A, the capacitor charges to the battery voltage. Move the switch to B, and the capacitor is disconnected from the power supply, though it is still fully charged. When the switch is moved to C, the capacitor will start to discharge through the coil, causing current to flow in this direction. Now, as you know, when current flows through a coil, the field about the coil expands as current increases. So as long as current increases, the field continues to expand. At the point when the charge on the capacitor is almost depleted, the amount of current begins to decrease. At the instant current begins to decrease, the coil will oppose this change. That is, the field will begin to collapse, reversing direction, thus reversing the polarity of the induced voltage, causing current to flow in the same direction. Or the coil becomes the source as the energy stored in the magnetic field is put back into the circuit, causing the capacitor to charge in the opposite direction. Now, when the field about the coil is completely collapsed, current is zero, and the capacitor is charged in the opposite direction, and it will again discharge through the coil. As current begins to increase, the field about the coil expands. Now notice that current is flowing in the opposite direction. So we'll show this on our graph. At some point, current will begin to decrease. And when it does, the magnetic field will start to collapse, reversing direction and returning energy to the circuit, which will cause the capacitor to recharge in the original direction. Now, when the coil's field is completely collapsed, current is zero and the capacitor is charged. Notice that the current on this alternation was not quite as great as the original alternation due to the circuit resistance, which we have not shown in this simplified drawing. Thus, as this oscillating action continues, the output waveform will continually decrease until the energy in the circuit is completely absorbed. The current waveform generated by the LC circuit looks very much like the graph of our mechanical oscillator. Why did the amplitude of the oscillations decrease? In the mechanical oscillator, inherent resistance or friction. Now, if we apply this reasoning to the LC circuit, it's obvious that the decrease in amplitude is caused by internal circuit resistance. That is, the resistance of the wire finally dissipates all of the energy. Now, we'll represent this resistance here. The amount of internal resistance will determine the quality of the circuit. And you should recall that the Q of a coil is equal to X of L over R. Thus, the higher the Q, the longer the circuit will oscillate because there's less energy dissipated in the circuit. But even the highest quality components offer some resistance. So to generate a waveform of constant amplitude, energy must be added to the circuit at the same rate that it's being lost, in much the same way that we fed energy to the mechanical oscillator. The ringing action of the LC circuit is often referred to as the flywheel effect, because like a flywheel, once it's started, a small amount of energy added at the right time and in the right direction will keep it going. And also like the flywheel, if energy is added in the wrong direction, the flywheel will stop. So energy must be added at the right time in the LC circuit. For example, if a positive voltage were applied at time 2, the energy lost in the first cycle would be replaced and the amplitude brought up to the desired value. If energy were added every cycle, we could maintain constant amplitude. However, if this positive voltage were added at time 1, it would cancel the energy in the circuit, and the circuit would stop oscillating. Thus, like the flywheel, the energy fed to the LC circuit must be of the proper amount to overcome the resistive losses in the circuit, and it must be delivered at the right time, or in phase with the oscillating signal. Now, the way this is usually accomplished is through an amplifier. The frequency determining device provides an input to the amplifier. The amplifier must provide enough gain so that part of the output can be fed back to the input LC circuit to sustain oscillations, and of course, provide enough signal for an output. Now, the energy must be fed back in phase or regenerative. Now, because many amplifiers shift the phase of the signal by 180 degrees, there may be phase shifting networks required in the feedback path. Various methods are used: RC, LC, RCL, or transformers between the output and the input. Now, which system is used will be determined by the type of oscillator circuit and its application. The important thing is that the energy fed back be in phase with the signal generated by the frequency determining device. This demonstration will convince you that feedback does occur and will cause a circuit to oscillate. The microphone here is connected to the input of the audio amplifier. The speaker is connected to the output. Between the two, I have a piece of acoustical tile. If I remove the tile and allow the microphone to pick up some of the output sounds, the amplifier will go into oscillation. Now, even though this circuit is not designed as an oscillator, if we feed the output to the input or develop feedback, it will oscillate. And if you've ever tried to listen to a PA system that has been plagued with feedback, you'll agree that in this case it is undesired. But before we go into what is happening in the amplifier, let's be sure we understand why it oscillates. Any sound picked up by the microphone is fed through the amplifier and out the speaker as sound. If the microphone picks up the sound coming out of the speaker, the output is feeding the input and the stage oscillates. Now, since there's no way to control the amount of feedback, the strength of the oscillator signal continues to increase. You can hear this increase when we remove the tiles slowly and allow the microphone to pick up the speaker's output. The squeal builds from a relatively low level to a very high level. And if allowed to continue, very high oscillating currents are built up that may damage circuit components. For this reason, the amount of feedback must be controlled in an oscillator. The correct amount is just enough to overcome the losses in the circuit. Any amplifier will oscillate if feedback occurs. But what is the frequency of oscillation? In the LC circuit, we found that frequency is determined by L and C in the tank. Now, the same thing is true in the amplifier that oscillates. But since there is no frequency determining device, the frequency of oscillations is determined by distributed L and C. That is, the input capacitance of the amplifier, the inductance of the leads, or any inductors and capacitors in the circuit. Very difficult to predict the frequency. And thus we see the need for a frequency determining device. In this case, the LC combination. These component values are carefully calculated to oscillate at exactly the right frequency. Then the exact amount of feedback. And we have an LC oscillator that provides a signal of constant frequency and amplitude. One other factor should be considered, and that is loading the oscillator circuit. We can see this effect clearly by looking again at our basic circuit. We've already pointed out that the feedback overcomes the loss caused by the internal resistance of the circuit, which is small when a high Q tank is used. However, there is another quality factor that concerns external circuit resistance, and in this case, the resistance should be high. In other words, the amplifier connected to the frequency determining device should offer maximum impedance to the tank. Even then, there will be some energy loss to the external load, which must be regained by increasing the feedback. Now, because loading and power surges can cause shifts in amplitude and frequency, the oscillator stage is usually isolated from the rest of the equipment by special amplifiers or other circuits. Now, the exact kind of isolation depends on the particular application or use of the oscillator. However, there are several basic oscillator characteristics that are always true, whatever the type or application. First, any oscillator should develop a stable frequency and a signal of constant amplitude. Now, be sure you understand that this statement applies to all oscillators, the LC or any sine wave oscillator, as well as the sawtooth, square, rectangular, or trapezoidal oscillators. All of them should generate constant amplitude and frequency. Now, here's a list of the basic requirements that also applies to all oscillators. First, of course, a DC power supply. It may be a simple battery or a very complex, carefully regulated circuit. Next, a frequency determining device. We have seen that an amplifier will oscillate without a frequency determining device. But the frequency is determined by distributed LC, which makes frequency difficult to calculate and erratic. This kind of oscillation is usually undesirable. A frequency determining device, in this case the LC tank, provides a stable, easily calculated frequency. Feedback is required to sustain oscillations in the frequency determining device and is usually accomplished with an amplifier. The frequency determining device provides an input to the amplifier, and the amplifier must provide enough gain so that part of the output signal can be fed back to overcome resistance in the tank and replace any energy lost through loading. Of course, the feedback must be regenerative or in phase. Thus, a phase shifting network between the output and the input may be required. There may be other requirements depending on the application of the oscillator, which you'll discover when you study a particular piece of equipment. But the main idea is that all oscillators are basically the same. So whatever the type or the name of the circuit, all oscillators will require a power supply, a frequency determining device, feedback, usually from an amplifier. Now, if you apply these basic principles, oscillators will be much easier to understand. Just like this clock, the spring drives the gears that feed energy to the pendulum, which is the frequency determining device. And thus, the pendulum moves at a constant frequency and amplitude, which, of course, is the purpose of any oscillator.